Hello and welcome to this video on enthalpy changes. This is for OCR A. My name is Chris Harris and I'm from AlleryTutors.com, and basically we're just going to go through the enthalpy changes topic as part of OCR A, like I say. These slides that we're using here are available to purchase. If you just click on the link below in the description box and you'll be able to get them from there. Okay, so yeah, like I say, this video is specifically for OCR A, and you can see it'll meet the specification points that are on display now. Okay, so we're going to look at enthalpy first. We're going to say, what is enthalpy? So when a chemical reaction occurs, there's normally a change in energy. Okay, and so the enthalpy change of a reaction is the heat change in a reaction at a constant pressure. Okay, so that's what we're looking at. So it's given the symbol delta H, and it has the units of kilojoules per mole, or kJ mole to the -1. And it's given this symbol here. You can see the Greek letter is a triangle. It just means delta, means changing. So basically we're looking at the change in enthalpy. And the little underground symbol here, this means under standard conditions. So standard state under standard conditions. So everything is basically kept constant, so we can compare them. And the standard conditions are 100 kilopascals of pressure and 298 Kelvin, or 25 degrees Celsius. Okay, so let's look at exothermic and endothermic reactions. So reactions can give out heat energy or take it in. So endothermic reactions, these are reactions that absorb energy from the surroundings. So for example, the products in this reaction are higher in energy than the reactants, and delta H is positive. So you can see here, there's the energy required to move from reactants to products. Products are higher in energy, so this is an endothermic reaction. Energy is taken in to produce your products. Okay, and you can see here that we've got an activation energy as well. This is the energy profile of the reaction, and so basically this bit from the reactants to the top of this energy profile is called the activation energy. We'll look at that in a little bit more detail. So an example of an endothermic reaction is calcium carbonate, decomposition of calcium carbonate. You'd form calcium oxide and carbon dioxide, and obviously the enthalpy change of combustion in this case is endothermic, plus 178 kilojoules per mole. Okay. Exothermic reactions, these are the opposite. These release energy to the surroundings. So your energy profile diagram is basically looks like this. So your reactants are higher in energy than your products. Energy is released, so it's delta H is negative, because our products are lower in energy than our reactants. And there's our energy profile, our diagram. Again, we're going from reactants to the top of this energy profile here. We'll go into activation energy later, but basically this green arrow represents the activation energy on this energy profile. An example of an exothermic reaction is ethane, burning it, which is combustion of ethane, and we produce water and carbon dioxide, and this is enthalpy of combustion because we're burning it again. So this is going to be minus 1560. Obviously we're burning a fuel, so it's going to be exothermic. We're going to produce heat. Okay, so know your delta H's. Okay, there's 4 types of enthalpy change that you need to know. You've got enthalpy change of reaction with a little r there, so delta RH with your little underground symbol. The enthalpy change of reaction according to the molar quantities in the equation under standard conditions. Okay, so this is just the standard reaction. Delta Newt H with the underground symbols, it's theta. I should stop calling it out really. It's the standard enthalpy change of neutralization. So this is basically the enthalpy change when an acid and alkali react to form 1 mole of water under standard conditions. Very, very important. Okay, make sure you know these definitions. The next one, standard enthalpy change of combustion. So this is the enthalpy change when 1 mole of a substance is completely burnt in oxygen to make carbon dioxide and water under standard conditions. So all of these are gases basically. So make sure you know these definitions are so important. Okay, completely burned, 1 mole of substance is completely burnt. And the final definition you need to know is the standard enthalpy change of formation. This is the enthalpy change when 1 mole of a compound is formed from its elements in their standard states under standard conditions. Okay, so you'll see these being played out later on in the video. Okay, so bond breaking and making. So bonds are broken and made during a reaction. Obviously, we're reacting these things. We have to break some bonds. So bonds are broken. Energy is needed to break bonds. So the energy is actually absorbed. And because energy is needed, this is an endothermic process. So delta H is going to be positive. So let's go back to this energy diagram again. You can see delta H is positive in endothermic reactions. More energy, if more energy is needed to break bonds than energy given out when the bonds are formed to produce your products, overall the reaction will be endothermic. And let's look at bonds made. So this is when bonds are formed, energy is released. So obviously, because it's exothermic process, delta H is going to be negative because obviously this is exothermic. Here's our energy level diagram here, and you can see that this is obviously showing an exothermic process. And again, if more energy is released when bonds are formed than what was needed to break the initial bonds, the reaction is going to be exothermic. Okay, so the energy needed per mole to break attractive forces in a bond in bonds is called bond dissociation enthalpy. So just be aware of that. It's the amount of energy per mole to break these attractive forces. This only happens in gaseous compounds though. Okay, so as long as you're aware of that, you need to know about bond dissociation enthalpy. Okay, so mean bond enthalpy. Right, so bonds of the same type don't all have the same amount of energy, which may sound a little bit strange, but actually it's pretty logical when you look at it. So let's say we've got 4 CH bonds in methane. Okay, they all have slightly different bond enthalpies. The energy needed to break the first CH bond will be different to the energy needed to break the second CH bond. So therefore the energies are obviously different, depending on which one you're going to break first and which one you're going to break second. So what we can do then, because it's a bit confusing, we have all sorts of different energy values for the same bond. We can measure the enthalpy values at the energy of breaking all 4 bonds to get the amount of energy needed to break all 4. And then what we can do is divide them by 4 to get a mean bond enthalpy. So it's an average bond enthalpy. Okay, so the total for this case is 1,662 kilojoules. That's for 4 CH bonds. So the mean bond enthalpy is basically of just 1 CH is that number divided by 4, and so this is going to be 415.5 kilojoules per mole. Now that's the mean bond enthalpy for a CH bond. And enthalpy changes using mean bond enthalpy. So we're going to look at an example. We need to know this formula. This formula is enthalpy change equals total energy needed to break the bonds minus total energy released forming the bonds. So let's have a look at an example. Calculate the energy change for combustion of methane. Here's methane. Burning it with oxygen or combining it with oxygen to form carbon dioxide and water. Here's the data. Okay, so we've got the bond enthalpies here. There's all the enthalpy values there. Look, in kilojoules per mole. This is mean bond enthalpy. C double bond O, CH, O double bond O, and OH. Okay, so we need to be able to work out the total amount of energy needed to break all of the bonds in all of the reactants. So we've got 4 lots of CH because of the methane. So that's 4 lots of 435. Is 1740. We've got 2 lots of O2, so we're going to do 2 times by 498, which is 996. So add them up, and the total should be 2736 kilojoules per mole. It's the total amount of energy needed to break the bonds. It's an endothermic process. Then we need to work out how much energy is released when we form these bonds here. So we've got 4 OHs, because we've got 2 water molecules, 4 times 464, 1856, and we've also got 2 lots of CO, which is the carbon dioxide, because remember it's 2 lots of CO, 2 times by 805, and that's 1610. Okay, so all these, add them up, 3466 kilojoules per mole. So there's actually more energy being given out when we're forming these bonds than what was needed to break them in the first place. So overall, this thing is going to be exothermic. If we put it into our equation, total energy to break bonds minus total energy released, so that minus that, and that gets you minus 730 kilojoules per mole. And it is, look, it's negative. And that would kind of make sense because this is just combustion of a fuel, and fuels obviously produce energy. So if you get a positive there, obviously you don't burn a fuel and get colder, it gets warmer. So just check your signs. Okay, calorimetry. So this is a practical technique. So calorimetry is used to work out the enthalpy change of combustion of a fuel. Okay, so what we've got is a fuel is burnt to raise the temperature of water by a specific amount. Okay, so generally we weigh the fuel before and after, and basically we're trying to work out the mass of fuel that has been burnt. So the energy from the fuel is transferred into the water. However, some of it is lost to the surroundings, so the flame might flicker in the wind, and you might get some of the energy heating up here and heating up here. Some of it might be absorbed by the tripod. Some might escape from the water out. Obviously, we'll put a lid on to try and stop that. Some might escape into the container. So it's really difficult to do, but I want to try and get everything, all the heat from here into the water. So yeah, like I say, the lid's placed on top to try and stop heat loss. You can put draft shields either side as well to stop the flame from flickering around if it's drafty in the room. And basically, we can work out the energy transferred by using this equation. Q equals MC delta T. Okay, so we're going to see that a little bit further. And basically, we can use this value of energy, Q, to work out an enthalpy change. There's a difference between energy and enthalpy, as you'll see. Okay, so let's have a look at a calculation. So energy from a calorimetry experiment can be calculated. So let's bring this equation back in. Q equals MC delta T. Okay, Q is the heat energy lost in or gained. So this is in joules. Energy is in joules, remember. M is the mass of water in the solution, which is in grams. C is the specific heat capacity. You'll get this in the exam, 4.18 joules per gram per Kelvin. And delta T is obviously the change in temperature. Now this must be in Kelvin. Temperature change in degrees C is the same as the temperature change in Kelvin. So it doesn't really matter if you don't convert. Okay, so this example, 100 grams of water was heated from 23 degrees Celsius to 57 degrees Celsius by 1.8 grams of ethanol. Calculate the energy transferred and hence the enthalpy change of the fuel. All right, okay, so let's have a look. The first thing we need to do is basically work out the energy first. So Q is energy, remember. M is the mass of water, 100 grams, so 100 grams of water, times by 4.18, because that's the heat capacity, times by 34, which is the change in temperature, 57 minus 23. Get the value, and this will be in joules, 14212. Let's convert it to kilojoules, because it just makes it easier. 14.212 kilojoules of energy is being given out. But we need to work out the enthalpy change. Enthalpy is different to energy. Okay, so to work out enthalpy, remember enthalpy is in kilojoules per mole. We need to work out the moles of fuel that was used to heat that water in the first place. So the moles of ethanol is mass over MR. Now we know the mass of fuel is 1.8. So do 1.8 divided by the MR of the fuel, which is 46, gives a total number of moles of 0.039. So now we have the number of moles. We can basically do, because remember the units of enthalpy is kilojoules per mole, we do that divided by that. So let's go for it. There it is. Enthalpy is energy divided by moles minus 14.212, because this is exothermic, remember, this is a fuel, divided by 0.039, and that gives you an enthalpy change of minus 364.4 kilojoules per mole. It's as simple as that. Work out the energy first, work out the moles of fuel, work out your enthalpy. It's like 3 stages there. Okay, another type of calorimetry. So this one, instead of using a fuel, we're going to do the calorimetry, the energy change of a solution, for example, a neutralization reaction. So here we've got a polystyrene cup, and that's basically there to prevent any heat loss. We're going to add our acid first, and we're going to measure the temperature of the acid for a fixed period of time. Maybe it's 3 minutes or 4 minutes, sometime like that. Okay. Then we're going to add our alkali or solid and stir, and then we're going to measure the temperature change. Okay, so let's look at this example. 25 centimeters cubed of 1 mole per dm cubed HCl had a temperature of 20 degrees C. 25 centimeters cubed of 1 moles per dm cubed of sodium hydroxide was added, and this raised the temperature to a maximum of 26 degrees Celsius. Calculate the enthalpy of neutralization for hydrochloric acid. Okay, so just like the one before, we have to work out the energy first. However, you've got to be really careful here, because instead of using the mass of water, we've actually got just 2 liquids here. So to work this out, we have to take into consideration both liquids. 25 plus 25. Add them up, and that's 50 grams in total. Okay, this is assuming a density 1 gram per centimeter cubed. Times it by your 4.18, it's your heat capacity, times it by 6, which is the temperature change. 20 minus 26 is 6. Put your numbers in, we get that in joules. That's in kilojoules, 1.254 kilojoules. We want to work out an enthalpy of neutralization. So what we need to do is we need to work out the number of moles. Now, because we've already used our acid first, then we're going to work out the moles of acid. Concentration times by volume to work out that. So the concentration is 1 times by the volume, which is 25, times by 10 to the minus 3. We get this bit because that just means divide by 1,000. So remember, our volume is in 25 centimeters cubed. This has to be converted to decimeters cubed. So we divide by 1,000. I just put that on there because it's just a bit neater. And then we get the number of moles of HCl to be 0.0250. Okay, so this is the number of moles of HCl that we are going to be using. Okay, because we're working out the enthalpy of neutralization for hydrochloric acid. Then once we've got the moles, we then do exactly the same as before. Enthalpy is energy divided by moles, kilojoules, remember, minus 1.254. That's what we worked out there. It's exothermic. Remember, it's an exothermic reaction. It's raised the temperature. Divided by the number of moles, which is just worked out there. We should get an enthalpy change of minus 50.16 kilojoules per mole. And that's pretty much it for your calorimetry calculation. So make sure you be able to kind of watch out for this particular bit here, because some people might forget that. Okay, right, Hess's Law. Okay, so we've got this fella called Germain Hess, and he came up with a law to work out the enthalpy changes that you can't find out by doing an experiment. So this is pretty handy. And he came up with this law. It's so important, I've put it in the biggest writing on the screen possible. So we've got Hess's Law is the total enthalpy change of a reaction is independent of the route taken. Okay, and you'll see what that means later on. Might be nothing at the minute, but we'll see what that means. Right, so let's look. We've got two main cycles here. We've got formation cycles and combustion cycles. So let's look at the formation one first. So if you're given formation data, you draw a formation cycle. Okay, so this is an example of data that is formation data. So the data they've given, you can see here, enthalpy of formation and the information there. So the cycle is pretty straightforward. We have reactants and products like a normal reaction here. Reactants and products. The arrow here can represent enthalpy of combustion or reaction. It depends what they're asking you in the question. Okay, so we've got red and green. Try and colour code this. Right, and a formation cycle is always elements in the standard states at the bottom, arrows pointing up to your reactants and products. And obviously this works out your enthalpy of formation. It must be in that order to make sure that everything works out properly. Okay, arrows pointing up with elements in the standard states at the bottom. So what we're going to do is we're going to substitute these numbers here in the spaces where it says enthalpy of formation. And we need to multiply the number of moles in the equation as well, so when we get the equation. So let's look at an example, a specific example. So when we go with the arrow, we keep the sign the same, as you'll see later on. And when we go against the arrow, you change the sign. So we're going to calculate the enthalpy of combustion of methanol, burning completely in oxygen to make carbon dioxide and water. So you can see here, we've got our formation data there. Here's our reaction. Methanol plus oxygen will form carbon dioxide and water. Okay, so the first bit we need to do, write our elements that make up these. Elements are carbon, oxygen, hydrogen, O2, H2. Balance them, make sure we've got the same number of elements as we do reactants. Okay, then we're going to swap our numbers in. So enthalpy of formation of methanol is minus 234. We've got one of them, so that's fine. Enthalpy of change of oxygen is 0. Enthalpy of formation of elements is always going to be 0. We've got 0 here and 0 here. It's O2. It hasn't changed. It hasn't changed from here to here, so it's 0. So the total on that side is minus 234. We take our attention onto the other side now, and then we're going to work out the enthalpy of formation of carbon dioxide is minus 394, because we've got it there. The enthalpy of formation of water, because we've got two of them, we have to do two lots of minus 286, which gives us minus 572. Stick our total in, minus 966. That's the enthalpy of formation. We want to work out the enthalpy of combustion, because that's what it's talking about. So basically, this is where the arrow bit comes in. So we want to go from here to here. We can't do it. Imagine that's a roadblock. So the diversion we take is going down here and then up here. So we go against A and with B. Okay, so you can see we've written that down here as a summary. So we'll go against there. So we swap the sign, plus 234, as you can see here, with the arrow there. So we keep the sign the same, minus 966. Put that in your calculator, and we should get minus 732 kilojoules per mole. And that fits, because this is combustion of a fuel. It's exothermic. It's minus. Okay, and a quick way to test, start anywhere on that cycle. And basically, if you add it up, remember, if you go against the arrow, you flip the sign. If you go with the arrow, you keep the sign the same. it should add up to 0. It's independent of the route taken. That was Hess's law. Okay, let's look at another cycle. This is combustion. There's only 2 cycles. So if you're given combustion data, you draw a combustion cycle. So here's an example of some combustion data. Look out for that bit in the data. So this one, reactants or elements, depends what reaction they're giving you, and forming products. Enthalpy of formation or enthalpy of reaction on the top. Now, combustion cycles always have combustion products at the bottom. Carbon dioxide and water, we assume it fully combusts. Enthalpy change of combustion is obviously on there, and notice the arrows are now pointing down for enthalpy of combustion for the combustion product. Okay, so remember what we have to do, just like with the formation, substitute your numbers in where these bits are, and then multiply by the number of moles in the equation. So let's have a look at a specific example. So remember this rule, go with the arrow, keep the sign the same, go against the arrow, you change the sign. So we're going to calculate the enthalpy of formation of pentane from their elements and their standard states. So we've got obviously our enthalpy of combustion data, so we know it's a combustion cycle. Here's our elements and their standard states. There's pentane and oxygen. So the first bit we need to do is write our combustion product, make sure they balance, 5 carbon dioxide, 6 waters, and we're going to use this information here to fill in the cycle. So we've got 5 lots of carbon, which is minus 394, it's minus 1970. We have a H2, but we've got 6 lots of H2. So there it is there. So it's minus 286, so it's minus 1716. So the total for this side, remember oxygen we don't count. In fact, we can cancel oxygen out left and right, because obviously we've got oxygen on the right and on the left, so we just ignore that. So enthalpy of combustion is minus 3686. Let's look on the other side now. Enthalpy of combustion of your pentane is minus 3509. We only have one of them, so that's fine. The oxygen we can ignore, so the total is minus 3509. We can ignore it again because we can cancel them out there. We want to work out the enthalpy of formation, which is this bit here. Again, when we're doing the cycle, we need to go from here to here, but imagine that's a roadblock, so we can't do it. So we're going with the arrow here and against the arrow here, so we're taking that diversion. So with A means minus 3686, and against B is plus 3509, equals minus 177 kilojoules per mole. So this is basically the enthalpy of formation of pentane, minus 177. So this is an exothermic reaction. Okay, again, put your numbers in, start anywhere on this cycle. With the arrow changes, keep the sign the same. Against the arrow, change the sign. Add it all up, should add up to 0. And that is it. That is basically an overview of the enthalpy changes part that you need to know for OCR A. Please support this channel by subscribing to it. If you just click on that circle there, and you keep up to date with all the new videos that we put on, and just remember that if you want to purchase this slide, if you like the look of it, then if you just click on the link in the description box below this video, and you can get access to it there. But that's it now. Bye bye.